if 0 is an eigenvalue. So suppose 0 is an eigenvalue. Oh, by the way, guys, I'm going to be writing the word eigenvalue and eigenvector a lot. And so I propose a shorthand. Okay? So maybe I'll do that first, and then we'll start. So for the shorthand, and I remember when there was a teacher that I knew that proposed this, I thought it was a great idea. EV is going to be eigenvector. EW is going to be eigenvalue. And you might say, well, what's the deal with that? They're both V's. But the reason is because the word eigenvector comes from the German. And I learned this when I was doing my research. You had to show mastery of one language. Not that I could speak German. I can't. But the idea was, if they gave you a German math paper, could you translate? We had to pick between German, Russian, and French, because a lot of the great mathematicians we knew of were from those nationalities. Of course, then it was kind of silly, because we had all these students that were at Case from China. There's a lot of good Chinese mathematics also. And they didn't have the language requirement, because they had to learn English. That was their language requirement. So my year, I actually signed a petition, because one of the big papers in my field of research, on the field of values, it's called, of a matrix, it was written in German, and it was really long. It's like 30 pages? I don't know. So I asked, hey, if I translate this into English, so my colleague and I worked to translate it into English and publish it, could that take the place of the test? And they had their big meeting, and they said, sure, that'll take the place of the test. Then the next year, they got rid of the requirement. No other math PhDs had to demonstrate language proficiency anymore. But anyways, German for eigenvector is eigenvector. With a K there, it's not that big. But German for eigenvalue is eigenwert. But that's the word value, with a W, although they pronounce it V. So is this okay for shorthand? So here we go. That took a minute, but it'll allow us to write more quickly from now on. Suppose 0 is an eigenvalue, so I'll put EW, of a matrix A. I guess my question is, what does that tell me? Well, what's the only equation we really have about eigenvalues? Again, the only thing I knew about eigenvalues when I was your age, AX equals lambda x, right? But in our case, what does that mean? AX equals what? Yeah, 0x, which is the 0 vector, right? Can you guys follow that? So if you think about that, if 0 is an eigenvalue, any eigenvector associated with lambda equals 0 is in the null space of A. Right? Because that's their equation for the null space. AX equals 0. Okay? So actually, if we look at the quiz question that we had, they said a few different things that might be true. Okay? One thing they said was, and this was interesting, I thought, they said there are infinitely many solutions to the system AX equals the 0 vector, right? Do you see why that's true? Well, what are the only possibilities to a system of equations? You either have infinitely many solutions, or what else? One or 0, right? But if we have a system like this, homogeneous, you have to have at least one, because what automatically the 0 vector solves it. And so if I'm saying this is an eigenvalue, that means there's eigenvectors that go with it. And 0 can't, the 0 vector is not an eigenvector. That's not interesting. It's only interesting when there's non-trivial solutions. And so that's why this one is equivalent to 0 being an eigenvalue. But this one was already in the fundamental theorem of invertible matrices, right? So maybe that explains a little more about how 0 being an eigenvalue is the same as not being invertible. Yeah?
Is that saying that like the solution could be, you know, like any vector, but since the eigenvalue is 0, you multiplying that by the vector will get you to 0?
Yeah, now I guess what I'm saying is, yeah, there are going to be, it's not any vector, but if you have a solution, yeah, it's in the null space. And we've computed the null space of matrices before, right? There are some vectors that are in the null space of a matrix. Yeah.
Since eigenvalues are the main diagonal entries of a triangular matrix.
Of a triangular matrix, yeah.
So could you also use that to say the same thing, because you'll have the free variable if it's in reduced echelon form?
So that's interesting. Suppose A is upper triangular. So let me take my favorite matrix. Well, that's not upper triangular, right? 1, 2, 3, 4. Oh no, I can't make that. To make it upper triangular, this has to be a 0, right? 5, 6, 0, 0. Now, if I put a 9 there, it's upper triangular, right? So I could compare this matrix in green to maybe this matrix. 1, 2, 3, 0, 0, 6, 0, 0, 9. There we go. So I think what you're getting at here, Tyler, is that what are the eigenvalues of this matrix? 1, 5, and 9. But what are the eigenvalues of the blue matrix? 1, 0, and 9, right? And so you would tell me the blue matrix does not have an inverse. The green matrix does have an inverse. You could see that because it's upper triangular. But I guess, let me go back to my favorite matrix. Do you guys remember this one? 1, 2, 3, 4, 5, 6, 7, 8, 9. Does this one have an inverse? Well, it's my favorite, not yours. You remember, Anthony?
I don't think so.
It doesn't. We just did something with my favorite matrix last class. We computed the determinant. Do you remember what the determinant was of this matrix? It was 0. And that was another way of saying it doesn't have an inverse. Right? By the way, that was also on the quiz. Not just C, but A said, okay, suppose 0 is an eigenvalue of a matrix. Won't it be true that the determinant of A is 0? Yeah, that's going to be true. That's easy to see in the blue matrix, right? Because what's the determinant of an upper triangular matrix? It's just the product of the diagonal entries, right? So this one has determinant 0. You know it doesn't have an inverse. What's the determinant of the green matrix? 45. Which doesn't mean much, but it does mean that it doesn't have an inverse. That it does have an inverse. Okay. So, but what's the determinant of this one? That takes a lot more work to calculate. That we spent what, 20 minutes calculating this last time, learning how to calculate it. Okay. I guess the other thing about, Tyler, about what you're talking about, you mentioned, what if you reduce row echelon form your matrix, right? Unfortunately, okay, row ops change the determinant. So that's too bad, right? But on the other hand, it changes it in a predictable way. So we will study how it gets changed. And actually, you can use row operations to compute determinants. And so I'll just tell you that in section 4.2, which we didn't read yet, we're gonna talk about how that happens. So after break, guys, I'll talk about the relationship between determinants and row operations. But for now, we're going to kind of stay away from it. Okay. What was B? I can't remember. Oh, yeah. B, it says the columns of A are linearly, what do you think, guys? If I know there's infinitely many solutions, then the columns of A are linearly, do you guys know? Dependent. That's right, James. So again, my favorite matrix has linearly dependent columns. This one, actually, the blue matrix, you can see. What are the linearly dependent columns in the blue matrix? You can see them. Yeah, the first two columns, right, are clearly linearly dependent. One is twice the other. It's not so simple here, but we know that it's true. This one has linearly independent columns. Okay? So that's why that fundamental theorem keeps growing, is because we're learning more and more ways of kind of talking about, do we have a square matrix that's invertible, or do we have a square matrix that does not have an inverse? The word for that is singular. So, good. All right. So I think the thing to do now is to talk about how we compute eigenvalues and eigenvectors kind of in general. But actually, I think the other thing to do now is to do maybe the other half. Remember, do you guys still have that packet I handed out? The discovery worksheet? I think it's time for the other half. And if you guys want to use MATLAB, I think now would be a great time to do it. So we'll have two pairs, and we have MATLAB, and I'll send you to work on it, and we'll kind of go from there. Let's start with a review. I called it the big computation, right? Because I told you the only thing I knew about eigenvalues when I took this class was AX equals what? Yeah. But what I said we should do to both sides of this equation is subtract lambda x. So we get that. And when I write this second equation, that 0, is that a scalar or a vector? Vector, because Lx, lambda x is a vector, and Ax is a vector, right? So we get that. And you remember the next couple of steps here? Yeah, in order to take out the x, first I need to throw in the identity matrix here, right? And because lambda has to be with a matrix, so that what you have here are two matrices that you're subtracting, right? You can't subtract a scalar from a matrix, but you can subtract a matrix from a matrix. And so now I have a minus lambda I times x equals 0, right? And so basically, the start of this whole thing was x is an eigenvector of A, right? and lambda is an eigenvalue, right? That was the start of this whole thing. And so what does that really mean? It means x is in the blank. James, this is really for you because we were all here last time. If I say x, this matrix times x is 0, that means vector x, what can I say about it? It's in the blank space.
The null space.
That's right. The null space of what? Of the matrix A minus lambda I. You guys with me? So that computation leads me to a very important observation. It's this, guys. If I want to know the eigenvalues, I can solve the characteristic equation. What's the characteristic equation? People from here, from last time? Yep.
A minus lambda I
Equals 0. And that 0 is a number because the determinant is a number, right? So I'm telling you that for any of these problems, this is really one way you could start the problem. It was funny because the quiz said, don't find all the eigenvalues and eigenvectors, just kind of think. But now I want to show you how we find the eigenvalues and eigenvectors, because that'll certainly make things a lot easier. So for problem 4, right, on your group work, and so who did this one? This was you guys in the back? All right. So we had G was equal to 0, 1, 1, 0, right? And so G minus lambda I would equal, well, it's the same matrix, except that in the diagonal part, what are you going to have? You'll have negative lambda here and here. That's right. Okay? And so now, the characteristic equation, well, this is kind of interesting. How about I say this? No, I'll do it. Well, I'll say the determinant of G minus lambda I would be, now how do you do this? You do negative lambda times negative lambda, which would be lambda squared minus 1, and we're going to set that equal to 0, right? And so that teaches you very quickly that what are the eigenvalues of this thing? Well, you can factor it, right? So lambda equals negative 1 or lambda equals positive 1, right? We know the eigenvalues right away. And then, once you have those, how do you compute the eigenvectors? Well, we did that this way. So like if I want to know the eigenspace associated with negative 1, right? That is the null space of G minus negative 1I, right? Which is really the null space of G plus I, right? So how do you do this? Well, really, what you want to think about is you want to think about the null space of what matrix here? What would G plus I look like? I guess it would be 1, 1, 1, 1, right? So what you're going to do here, right, if you want to talk about the null space of that matrix, you can reduce row echelon form this matrix, right? Because the null space are the things that will give you zeros.
How do you get the 1, 1, 1?
let me slow down on that. I did G plus I, so that was this matrix, plus what's the identity matrix look like? Okay, so that's that. Guys with me? Hey, if you reduce or echelon form this matrix, what's it look like? Oh, it looks like this. So what's that teach you? Are there any free variables?
One.
There has to be one, right? Because there's, right? So basically what you do is you say, okay, x2 is equal to t, and then x1 has to be equal to, say, negative t, right? And so I could say, you know, that gives me basically t times negative 1, 1. Right? So I could say a basis for e negative 1 is given by the single vector what? Negative 1, 1. Okay? But it's funny because when they did the problem, they didn't have you do any of this. They just said, hey, can you come up with anything? Were you guys able to come up with any eigenvectors for number 4?
After first guess, 1, 1.
1, 1. And it turns out a basis for E1 is given by, like you said, 1, 1. So when that happens, that's a fixed vector, right? Right? Because 1 is the eigenvalue. So here are the two eigenvalues of number 4. And these are, well, the eigenvalues are negative 1 and 1. I already said that. The eigenvectors, you can get a basis for each of the eigenspaces this way. Okay? So 2, 2 would also be an eigenvector, but it's just a multiple of 1, 1. Does that make sense? All right, let's jump to number 5, which was the one you guys worked on, Mitchell and Tyler. And so for number 5, we have h is equal to 0, negative 1, 1, 0. And so what would happen if I want to do the same thing? I'll do the characteristic polynomial. Determinant of h minus lambda I. Well, that's the determinant of, it's almost the same thing, right? You just put negative lambda here and here, and you put a negative 1 here, and you put a 1 here. So what happens? You get lambda squared, what? Minus negative 1, right? And if that equals 0, we're trying to solve lambda squared plus 1 is 0. Guys, that doesn't factor. Right? Can you solve it, though? Can you solve for lambda? I mean, lambda squared equals negative 1, right? So what does lambda equal? I. Are there any other answers?
Negative I?
Is that true? If I square negative I get, yes, you get positive negative 1 if you want. So yes. Or another way to say it is, hey, when I take the square root of both sides, I have to remember to put plus or minus. Those are the eigenvalues. Again, they got at it a different way in the group work. They say, hey, find a fixed direction. Yeah, good luck. Were you able to find any or no?
Yeah.
Then it says, if you allow complex vectors and complex scalars, show that 1i is a fixed direction. Find a second fixed direction. Okay? And so you can do these things now in the same way that we just did, but these are the eigenvalues you need. You need to use complex numbers for some matrices, or else you're out of luck. So I'm going to pause and give my usual spiel about complex numbers, and then I'll come back to the recording. Again, I think this is important, guys. Look. Notice, for number 6, our eigenspace has dimension 1. What's that word mean, dimension?
The number of vectors.
Number of vectors in a basis, right? So my basis is a single vector. But that dimension is what's called the geometric multiplicity. Geometric multiplicity. Okay? This is the dimension of the eigenspace. Up above, when we did the characteristic equation, we saw that the algebraic multiplicity was 2, because you had this 1 minus lambda squared showing up, right? It was showing up twice. So there's a really nice fact that I think is important. The fact, it's a theorem really, but I'll just call it a fact. I don't want to prove it today. The geometric multiplicity will always be less than or equal to the algebraic multiplicity. And that's an important idea. Okay? So you knew right away this basis was either going to have 1 or 2 vectors, because the algebraic multiplicity was 2. So that's a really important fact. James? You have to look at the characteristic equation. The algebraic multiplicity is the number of times that that factor appears. So maybe it's over here, you could see it, right? This is lambda minus 1 times lambda minus 1. It appears twice, or 1 minus lambda times 1 minus lambda.
If it was lambda, like if it was lambda minus 1 times lambda minus 2, would that break it?
Yeah, matter of fact, we did that in number 4, right? Back your problem, let me go back to number 4. You guys had G. You worked this out. Each of these was algebraic multiplicity 1, both cases. Actually, what the fact tells me then is that the geometric multiplicity is also going to be 1, and that was the case. So you almost don't even want to think about it until you get repeated roots. That's when it gets interesting. Does that make sense to you guys? Okay. So I want to go back to maybe finishing the class, and we may even work on this after break some more, because this is an interesting problem. But number 3, right, you had this F, okay? So again, I can use MATLAB to do a few things. I already typed in F, right? And I even typed in V1, which is this vector. And so I can do F times V1, and I can show that that's a fixed vector, right? And then one thing that I can do now that I couldn't do back when you guys were working on this is I can say, hey, what's the characteristic polynomial of F? What does that mean, that set of numbers? Do you guys know? I'll show you. Oh, yeah? Yes. Yes. Yes, that's exactly right. Those are the coefficients of the characteristic polynomial, and it always starts with lambda to the whatever power, whatever n is. So here's all my work on this one. Lambda to the 4th, right, like you said. Now, Here's a big issue. How do you factor this thing? Good luck. Now, I will tell you, there are some tricks you can do. Like, I know that if it factors, it would be lambda minus something that goes into this. Either plus or minus 1 or plus or minus 5, if it's a nice rational number. It turns out, guys, that this is the characteristic polynomial for number 3. If you multiply this all out, you get that. Okay? What does this mean? What is the algebraic multiplicity of these two eigenvalues? 3 and 1, right? So this eigenvalue, right, lambda equals 1, has algebraic multiplicity 3. Okay? I don't have time to work out everything for you. Well, but luckily this is all done already. When I did lambda equals 1 and I found the basis, look at the funny computation. You end up getting 3 free variables. The number of free variables is also the same as the nullity. That's from the rank theorem. What did the rank theorem say? The rank theorem said the rank plus, yeah. So what's the rank of this matrix? 1. 1 plus 3 is 4, right? Well, if you have 3 free variables, R, S, and T is what I used, that means when you find a basis for E1, you're going to have 3 different eigenvectors in that basis. Does that make sense? So for problem 3, this tells me not only is the algebraic multiplicity equal to 3, but what else is true? The geometric multiplicity equals 3. You guys see that? So both things are true. Algebraic multiplicity and geometric multiplicity. Sometimes they're equal. Sometimes they're different. James?
Does that mean the number of free variables can determine geometric multiplicity? Or if there's 2 free variables, it's going to be a geometric multiplicity too?
Yeah. Yeah. And it's the free variables that happened when you plugged in that value of lambda. See, if I did f minus 5i, I'd have a different system. And I tell you, you'd only get 1 free variable because I know that the geometric multiplicity is 1. That's a good way to say it, James. I didn't think of that. Yeah. So